We continue our discussion on tutorial 5.25. So it is actually the idea of the effect of surface roughness on transition. So you could get it from page 387. So for example, air at 20 degrees Celsius and 1 atm flows at U equal 12 meter per second past a smooth flat plate. It is desired to trip the boundary layer to turbulence by stretching a 1 millimeter diameter wire across the plate at the wall, where will transition occur if the wire is placed at x equal 1 meter. So what wire location X will cause the earliest transition? So the idea of this one is something like this. So we have a flat plate here. So normally, as I said in the beginning of this lecture, so we will have a lamina and then turbulent. So to make the transition or make the turbulent occur earlier, we put something here. Okay, so this the object that we want to use is actually must not in a stable region. As I said, if we put in a stable region, it will back into lamina after the flow through the disturbance. Okay, that's why we need to know about the instability. We need to know the transition. Why? Because if we put wire that trip wire after in turbulent region, so nothing happened because the turbulent is already happened. Okay, so and then we have a value of k here. So the value of k here is actually the height of the wire. So because wire is circular, so we could take it as the diameter. But the idea is the height of the disturbance. That's why if after this in chapter 6, we will learn about the flat plate with a certain roughness, with a certain with rough flat plate. Okay, so as we know, if the plate is smooth, we could draw it like this one. So but if the plate is rough, so we could have some zigzag design like this one. So the zigzag design of this one, normally we will measure the height, okay, to reflect its roughness. So I think it is advantage for you to see what is the basic idea of roughness measurement, because normally we will have RA and sometimes it's RV or RP and so on. So it is actually to reflect the height of peak and also the valley of the topography for a certain surface. Okay, so this is the idea. Okay, this is at 20 degrees Celsius and 1 atm. We know that we are dealing with air. So because it is air here, so we could get the kinematic viscosity is 1.5 times 10 by the power of negative 5. So we take the simple value here, and the x is 1. So first we calculate the Reynolds number. So the Reynolds number is Ux over nu. So we substitute all the value. We could get it is 8 times 10 by the power of 5. So let's say we assume that it is a lamina boundary layer. So maybe we assume the transition is 10 by the power of 6. Let's say. So we assume this is still a lamina boundary layer. So and then we could calculate the value of delta star here. So the delta star is equal to 1.72x over Reynolds number, and this equation is actually come from the Blasius solution, because in this situation we don't know the velocity profile. So we assume that if it is lamina boundary layer, it is okay for us to use all the equation derived by Blasius, because Blasius is the representative equation for lamina boundary layer. So then we substitute the value of the Reynolds number. We could get the delta star here is equal 1.923. So and then at this position, a wire of diameter K equal 1 millimeter. And then we calculate the ratio K over delta star. So it is equal of 0.52. So this
Doctor,
is,
please.
yes,
Why we assume the Reynolds number is, sorry, the flow is laminar, and the Reynolds number is more than 5
5 times 10.
multiplied 10. Yes, yes, 10
Okay. So
power of 5.
so I don't know. So the reason is because if we assume that 5 times 10 by the power of 5 is turbulent, so means that the location here is cannot be calculated. Means that it is the effect of the tripwire is not there anymore. It is useless. Okay, just to answer this question, because this question is in our textbook, so I assume that maybe we could assume just to show you, because if I make this question for your final exam, so I will make sure that it less than 10 by the power of 5. Okay, this is just for sake to make sure that this question can be answered. Can you agree with me?
Yes, doctor.
Okay, because this question is come from the textbook.
Okay,
Okay.
doctor.
Okay. So just
Thank you.
assume. Okay. Just assume that the limit of the boundary layer is 10 by the power of 6 for this question only. Okay. Okay.
Thank
It
you,
is
doctor.
it is good if the location of 1 meter here is less than 10 by the power of 5. That's the best one, because it is a lamina. Okay. Okay,
Okay.
I'm sorry. I just answered this one because
No,
if I change the question, it's not a question from the textbook. It might be you are difficult to make a revision later on. Okay,
okay.
okay. So and then why we need to calculate this ratio? Okay, so because we need to solve this one by use the idea of this graph. Okay, because as I said, it is not easy to predict the turbulent behavior. So it's quite fluctuate very much. So we depends 100% with the experimental. So even now, actually, so and then from our textbook, we get, if you refer to figure 5.36, so we find that we have one graph like this one. So the x-axis is k over delta star, and the y-axis is the ratio between Reynolds number transition for rough over Reynolds number transition for the smooth surface. So if our calculation showing that k over delta star is 0.57 0.52, so let's assume that this is 0.52, so let's say it is almost 0.5. So we take a vertical line here, and then we take the value of y-axis, so it is around 0.4. So from this uh, graph, we could say that the uh, okay, so from this one, okay, we could have ratio Reynolds rough over Reynolds smooth is 0.4. So and then let's say from figure 5. Okay, so now we got we get that the 0.4 here, and we have the ratio between Reynolds number at rough times by Reynolds number at smooth here. So and then okay, so this is might be refer to the our textbooks. So let's say for the Reynolds number smooth, okay, it is assumed for that plate is a 3 times 10 by the power of 6. So we substitute here the Reynolds number smooth is 3 times 10 by the power of 6. So we get the Reynolds number transition here is 1.2 times 10 by the power of 6. So I hope you could understand the methods here. So the Renault number transition smooth here, if not given. So I think it is given. I will check the textbook. I think it is given here. So and then if not given, you can take it is 5 times the power of 5 times 10 by the power of 5. So if this question comes out in the final exam, I will make sure that everything is clear. Okay, this is just to show you the calculation method. Okay, so let's say we get the Renault transition is 1.2 times 10 by the power of 6. So and then we equate with the equation of Renault number ux over nu, and then we get it is x is 1.5 meter. So we found that the transition is actually occur at a 1.5 meter by putting a wire on the plate. Okay. Okay, so let's say the for smooth plate, the transition usually occur at 3 times 10 by the power of 6 here. Okay, so according to that, there's this specific condition. So and then if we equate with the Renault number ux over nu, so the transition mean the changes between lamina to turbulent boundary layer will occur uh, normally without any disturbance at 3.75 meters. So means that if you put a wire there, so the transition occur at 1.5. If you not have a wire, so the transition will occur at 3.75 meters. So and then the question asks, what is the earliest transition occur when the wire cause the lowest possible value of Renault transition? And from the graph, we found that so the lowest one is 0.1, let's say, okay, according to this graph, and it will the ratio is 0.8. So the ratio of K over delta star. So and then we could do some reverse calculation. So we have the Renault number rough over smooth is 0.1. And we assume that the Renault number of smooth is 3 times 10 by the power of 6 here. And the rough will become 3 times 10 by the power of 5. So and then if we do the calculation here, so we have the K over delta star equal to 0.8. So delta star here is actually can be calculate by using the idea of Blasius, which the delta star can be calculated by using the idea of Blasius, which is 1.72 x over square root Renault. So we substitute the value, so we get x is equal to 398 k. K here is not kilo, so please don't times with 10 by the power of 3. So K is the value of the wire diameter. So this is the wire diameter, but actually the spirit, the idea is to actually to know the height of the roughness. Okay, because it is in circular shape, so we take as the diameter of the wire. So it is 0.001, so that so x will become 0.398 meters. So here we could conclude that a 1 millimeter wire placed at 0.398 meter would cause transition almost immediately downstream. So this is the earliest location where the transition can be occur, because might be 1 millimeter wire is quite thick. Okay, so and then it could create transition earlier. Okay, so we go for question 5.26. So repeat problem 5.25 means we have the plate with a trip wire, but now the free stream turbulence level is 1%. So we calculate again. by using the Reynolds number. So we get it is 8 times 10 by the power of 5. Okay, so I'm sorry. In this one, we assume it is a turbulent. Okay, I will change question previously that one. Okay, so because I think it's create conflict for this class. Okay, so let's say the t is equal to 1%. Okay, so we take t is equal 0.01, and then from the Van Dries and Blammer equation, so which is equation 5.44 from the textbooks, so we could calculate the Reynolds number for transition as this one. So we substitute the value of t is 0.01, so we solve it, so we could take the Reynolds transition is 5 times 10 by the power of 5. So if here the wire is too late, the transition has already occurred at Reynolds number 5 times 10 by the power of 5. So means here we assume that, okay, if the free stream velocity has 1% turbulent, so means the location of trip wire, if you still remember the question, so we have the trip wire here at distance of 1 meter here. Okay, so because the free stream velocity here, okay, already has 1% turbulent, so means uh, make the turbulent boundary layer occur earlier. So means that the location here is actually we have laminar, transition, and turbulent. So mean the location of 1 meter here is already inside the turbulent boundary layer. So means the location of wire is not in the laminar region. So it will it give no effect of the formation of turbulent boundary layer. Okay, let's say for equation for question 5.28. So repeat problem 5.19. If the free stream has a turbulent level of 4%, find the estimated transition Reynolds number by two different methods and compare. Okay, so this is the question for 5.19. So air at 20 degrees Celsius, 1 atm. So flow towards a wedge of half angle, 36 degrees, 36 degree. So and then we need previously we already estimate the transition Reynolds number, but now we have the turbulent level of 4%. And we get a value here. So we have an equation to be integrate. So this is the point from the problem 5.19. So we could get u is equal 4x by the power of 1 over 4, beta is 0.4, and lambda is 0.05. So the calculation is shown in problem 5.19. So, and then we also calculate this one, and we found that the lambda is greater than 0.04. So means that we cannot use Dunham, so we could use the Blammer. Okay, so and then this is for the turbulent. Sorry, for the turbulent, the free stream velocity that have a turbulent level. So, and then we estimate this one by using the Schmidt and Henningsen. So it's come from the equation 5.47. So the equation is here. Okay. However, the value of t here is in term of percentage. So mean if it is 4%, so we substitute with the number 4, the 4 here, not 0.04. So we just put a 4 here. So we can get, it is between 1,000 to 200, 1,000 to plus minus 200. So I just use the value of 1,200 and 1,400. So if you calculate this one, so you will find that the value of Reynolds transition is 90,000 to 122,500.